Okay, I've got a problem up here on the board, and you'll see lots of problems phrased like this in the textbook. Want to just remind you that the book does not, until chapter 5, introduce this integral notation that we've been using. They will introduce it in chapter 5, and it's standard notation, but they're going to just use words to describe things rather than using that integral symbol. So here we're asked to find all functions y such that y prime is equal to 3e to the x minus 2 over 1 plus x squared. Well, that means this is the derivative. I want all the antiderivatives. So I'm going to go ahead and use the integral notation because it's a nice tool for this. So we're looking for the indefinite integral, or the general antiderivative of this function. Okay. Now I'm just going to rewrite this. I'm going to notice that this 2 on top, I can pull that out front so that this is really just 2 copies of 1 over 1 plus x squared, which I recognize as the derivative of arctan. Now, if you can see that with the 2 on top, there's no need to pull that 2 in front, but a lot of people find it's easier to see if you sort of bump that constant to the front of the function. And then I can say, okay, so I'm going to get 3 copies of an antiderivative of e to the x, which is just e to the x, minus 2 copies of an antiderivative of 1 over 1 plus x squared, which is arctan of x, plus c. And that would give me all of the functions that have 3e to the x minus 2 over 1 plus x squared as their derivative. Now, I'm going to change the question. I want to find all functions so that y double prime is cosh x minus 3 over the square root of x. So now this is a formula for the second derivative. So I'm going to need to anti-differentiate or integrate twice in order to get all the way back to y. So I'm going to start by saying y prime will be the general antiderivative of cosh x minus 3x to the negative 1/2. So I'm just going to rewrite that square root of x on the bottom as the negative 1/2 power. And then I can go along. I can say these are subtracted, so I can use my difference rule. An antiderivative of cosh is just sinh minus 3 times, I'm going to use the power rule. So negative 1/2 plus 1 is plus 2/2, so that's going to be x to the 1/2. Divide by that new power, and dividing by a half is multiplying by 2. Then I get a plus c. So we've got sinh x minus 6x to the 1/2 plus c. These are all of the functions that could be my y prime. So these are the derivatives of y. Y then is going to be the indefinite integral, or the general antiderivative of this thing. Now, one thing that's important to notice, c is part of the formula for y prime. So I've got to get a term of c in the derivative, which means I'm going to have an antiderivative of that arbitrary constant in my formula for y. So I can't just take these 2 parts, take an antiderivative and then take another antiderivative and then throw on a c at the end. Every time I integrate, I get my constant of integration. So let's see what happens here. I can say an antiderivative of sinh will be cosh minus 6 power rule. So I'm going to raise the power by 1. That'll make it x to the 3/2. Dividing by that is multiplying by 2/3. Plus an antiderivative of c is c times x. C is a constant, so it's the slope. I'm looking for lines of slope c, and then plus an arbitrary constant. Now, I can't use c here because I used c here, and this is supposed to be plus an arbitrary constant. If I insist that this one has to be the same as that one, this one can be whatever I want, but then this one is determined. So I'm going to just use k. If I wanted to, I could call this C1 and C2. The names aren't important as long as they're different names. Okay. So this gives me cosh x I can just simplify this coefficient. That's going to become minus 4x to the 3/2 plus cx plus k. So notice that c ends up actually being not just a constant term, but that ends up being the coefficient in front of x in my final answer for these functions. Okay. So very important to recognize that that plus c kind of seems like something you just throw on at the end, but sometimes it actually ends up not being something you just throw on at the end because it appears in the middle of the problem, and then you've got to carry it through with the rest of your work. Okay, now so far with these examples, we've been finding all of the antiderivatives of a function. There are plenty of times when we want to find a particular antiderivative of a function. So let's suppose that v of t is velocity. So t is here standing for time. V of t is the velocity. And I know that the position at time 0 is equal to 2. Okay. And let's suppose that our velocity function is given by sine of t minus t squared plus 3. Okay. So, if I want to find the position function, so find a formula for position as a function of time. Okay. Now here, I'm looking for one function. I'm not looking for a family of functions. When I'm giving position as a function of time, I'm saying at this moment in time, the object is going to be exactly here. Not here, give or take an arbitrary distance in either direction, but exactly here. So I'm looking for one function as opposed to an entire family of functions. That's because I'm looking for the position function that's going to pass through this point, 0, 2. Remember we said that adding that plus c basically is doing a vertical transformation or vertical shift of your basic graph. So I need to find the c that's going to lift the curve that I get so that it passes through the point 0, 2. So I don't want to lift it too high so that it's above that, or too low so that it's below that. Okay. When I have something like this, where we've got the derivative essentially and a value, we call this an initial value problem. And that means we're looking for one particular antiderivative rather than the entire family. Now, I start by finding the family, because I'm going to narrow it down to it's got to be one of these guys in this family of functions, and then I can figure out which one it is. So I'm going to say position as a function of time is going to be an antiderivative of its derivative. So it's an antiderivative of the velocity function. So we're looking at the general antiderivative of sine t minus t squared plus 3 dt. Notice I'm using t as my variable rather than x, so I'm integrating with respect to t is how we would read that. So this variable here will always match whatever variable you have in here. Okay, excellent. So I'm going to say an antiderivative of sine. Let's see, if I went with cosine, the derivative of cosine is negative sine, so I'm going to want negative cosine. So we get negative cosine of t minus t squared. When I integrate that, that's just a straightforward power rule, minus t cubed over 3, plus 3, that's going to give me a plus 3t plus c. So this gives me the general form of my position function. This is infinitely many functions, and I know that my position function is one of them. Now what I'm going to do is use the initial condition to figure out what value of c gives me the function that I want. Okay, so I'm going to say that 2 was equal to the position at time 0. But the position at time 0 is what I get when I plug in 0 for t. So that's going to be cosine of 0 minus 0 cubed over 3 plus 3 times 0 plus c. That simplifies to 2 equals cosine of 0 is 1. This is going to be 0. This is going to be 0 plus c. C is going to be 1. So that's the constant that I need. And then don't forget to put the pieces together, because the answer to this question isn't 1. The answer to this question is the position function. So I would want to put the pieces together and say my position function is going to be this formula, negative cosine t minus t cubed over 3 plus 3t plus 1. So I plug in the particular constant that's going to make this go through the point that I wanted it to go through. Okay, we'll try some more initial value problems in the next video.